Hi, my name is Julia Silge, and I'm a data scientist and software engineer at RStudio. For those of you who have watched any of my videos, you may notice I'm in a different place. I've moved. I'm now in a different location, different house. And today in this week's screencast, we're using the data set from this week's episode of Sliced, the competitive data science streaming show on Twitch, to talk about the new release of Fine-Tune and how to use racing methods for tuning. XGBoost boosted tree algorithms work really well with the kind of data sets that are often used in competitions like that on Sliced, and a racing method is a great way to tune through a lot of different parameter combinations really quickly. So we will go through the data set that was used this past week, do a little bit of exploratory data analysis, then talk about how to tune an XGBoost model, and then how to make predictions with it on how to evaluate it, on testing data. So let's get started.
Okay, let's see if we can learn a bit about baseball. I honestly know almost nothing about baseball, so this will be an interesting experience, I think. There we go. All right, so let's read in this training data and see what we have here. I thought this was a really fun episode of Slice to watch, and as I was watching it, I thought this would be a great data set to be able to walk through how to train an XGBoost model using the recent release of Fine-Tune that just came out, and show how to use the racing methods that we have. So what we're going to be predicting here is this is home run. Let's do view here. So that's what we're predicting is home run. We've got info here on the launch speed and angle. And so when it is, let's see, it is NA, I think. When is it NA? If it is these are all hits, I believe. So we're trying to predict if a hit is a home run. So if it's a hit, we should have a launch speed and angle. So sometimes we know the launch speed but not the angle, and vice versa. So it's just missing data, I believe. This info is about where it is physically around home plate, on the X direction and the Z direction, how many balls or strikes there's been, outs when up, a number for the park, and all this. Okay, so let's do just a little bit of some brief EDA, and then we'll start on our model. So let's start by looking at that info on the physical info about where the hit was. So let's do is home run here, and let's use that stat summary hex to make a little hex map. I've been really feeling that lately. I really love these. And let's try like 10 bins here, and then we're gonna be I keep hitting that today. There we go. Scale, fill, viridis, continuous, like this. And we have got a nice plot here. So let's change this just a little bit. So let's make that labels equals percent, like this. And then what that label is, fill equals, that is the percent of home runs, like this. What did I do wrong? Labels, it scales like that. Okay, so this is on the on this is X and Y, X around, not Y, X around home plate, and then how far above it is around home plate. And so here we can see this is where we, in this area, this is where we have the most home runs, is around here. So you can see kind of this nice little gradient that we have here. Let's do the same thing for that info that we saw about the launch angle and the launch speed. Let's put launch angle on the x-axis, launch speed on the y-axis, and then leave everything else the same. So that's where we got a lot of missing data. Let's bump this up a number of bins. So this is pretty interesting. Like no home runs down here, but if you're right here in this sweet spot of launch angle and launch speed of it coming off, then that is where you get the home runs. So this, I bet, is pretty predictive, because look how high this percentage is. That's really high percent compared to this, right? So that's probably super duper predictive. And let's just make one more exploratory plot where we, for this time, we're not going to use any of that anymore. Let's take is home run. Let's say, for example, let's take balls, strikes, inning, like this, and let's pivot longer those balls to inning like that, so that we're going to have now a tidy data set, a long tidy data set. And let's make that a factor. Make name fact in order name, like that. And you know what? Let's make this a factor too. Mutate is home run. Let's use if else. We'll probably have to do as a logical is home run, like so. And so if it's true, we'll say yes. If it's false, we'll say no, like that. Like that. Okay, great. And then what we will do is, let's put this into a plot. So we're going to say value on the x-axis, and we're going to make a fill is home run. And then I'm going to make histograms here. So we're going to make them like transparent, so they're over on top of each other like this. So position equals identity, like this. And we're going to facet wrap. So we'll have 3 little histograms by name. I guess we can vars name. And the scales equals free, like this. Okay, so let's change bin width to 1, because it's like 1 ball, 1 strike, 1 inning. And let us change labs. So we can say x equals null, y equals not, well, that's fine. Let's make fill equals home run, like this, question mark. And let's also, there's a lot more not home runs than home runs, so let's make this after stat density, like this. Nice. Okay, so you can see that the home runs are more likely to happen when there are more balls, when balls are higher, when strikes are lower, and in earlier innings. So those are probably a little bit predictive, not as much as this launch angle, launch speed thing, which is, you know, an actual characteristic of the hit. So I guess that makes sense. All right, let's get started on this model. So I am going to load tidy models. I am going to, next I'm going to take this train raw. I'm going to do this business that I just did right here. Instead of yes, let's call it home run, like that. And let's also make it a factor. Is home run equals factor is home run. And then I'm going to pipe this to initial split, like so. I'm going to do strata is home run, like that. So I'm going to call this my baseball split. And then I'm going to make my baseball train by calling training on my baseball split. I'm going to take baseball test by calling testing on my baseball split. And then I am going to, I need to make my seed, set seed. Set seed. And now I'm going to make some folds. I'm going to do vfold. I'm going to make folds on my training data. I'm going to say is home run. And let's call that baseball folds, like this. Like so. And let's run all that. So now I have folds that are ready to go. Folds of resampling folds ready to to use for the tuning that I'm going to do. So I made this section I think of as your data budget. You have a certain data budget. You have to decide how you're going to spend it. And so we decide how much we're going to put in testing, how much we're going to put in training, and then how we're going to use resampling for the tasks that we need to do. So the next thing after deciding your data budget is feature engineering. So I'm going to use recipes for this. And if let's look at our training data again. What if I do this so I can get a little bit better picture here? Oh yeah, that's nice. All right, so let's make a recipe. So I'm going to predict is home run. I'm going to predict it with definitely the launch angle and the launch speed. I'm going to do that plate info, where it was around home plate. Here. I am going to also use that info about inning, balls, strikes, and the game date, like when was it during the year. I think I'll make week there. I'm going to get some info about the pitch. So let's see. So BB train. So if I look at so that's about the pitch. I think that's is that about the hit or the pitch? Not entirely sure. I'm gonna put it in. The pitch name, I think I could put in there. I'm gonna do the pitch, I'm not gonna count that because it's numeric. The pitch miles per hour. And then I think these information about the handedness of the batter and the pitcher, I'm gonna put in there too. So let's put these things in. Okay, so bearing, pitch, miles per hour. I'm going to do is pitcher lefty, is batter lefty, and then I'm going to say data is this training data here. So let's call this my baseball recipe, like so. All right, so now I need to start do some of my feature engineering. Let's handle that date first. Game date. I have a lot of options here. I could do like day of the week, month, year. I'm gonna try month and week. See if there's differences by month or week. And I'm gonna take away the date. You know what? I'm just gonna do week. Like that. I am going to say step unknown. So anything that's a nominal predictor, I've imputed it by just saying it's unknown. I'm now I'm going to convert any all my nominal predictors to dummy or indicator variables. I'm using one hot equals true, which I don't think I've talked about this on a video, but is actually probably the best option for XGBoost. And now let's talk about, now everything is numeric at this point. So let's say step impute median. I'm going to say this for all the numeric predictors. And you know what? I could do that. That'd probably be pretty good. I'm going to show how to do something a little bit fancier for these two that I know have a lot missing. Launch speed. So this means impute median for everything that's missing except for these two. And for those two, I'm going to try to impute using a linear model. So I'm going to say I do want to impute launch speed. I want to impute these two with a linear model, and now I'm going to say which impute with. And I'm going to say impute vars. And now I can put in here what do I want to impute with. Let's impute it with, oh gosh, I could impute it. Let's impute it with plate X, plate Z, pitch, miles per hour. Anything else I want to put in there? I wonder if I could do it with starts with BB type. I wonder if that would work. Let's give it a go. All right, and just let's see if I can do this. It's rank deficient because I think it's like those things are too close together, like they are measuring the same thing. So let's take it out. Okay. There we go. So that works. So that's our feature engineering. Let me add one more thing just for safety's sake. I'm going to remove anything that's near zero variance, like that. Okay, so it did remove two things here that are probably like other or unknown or something like that probably. Okay, so that's my feature engineering. And now let's talk about the model specification. So I'm going to say XGBoost spec here. I'm going to say boost tree. And I'm not going to tune everything this time. I'm going to tune enough though so that we can see how cool it is to be able to use the racing method. I'm going to tune trees. I'm going to tune min n, like the minimum number of things to split. And I'm going to tune M try. I'm not going to tune the learn rate. I'm going to set it kind of medium here, big-ish, so that it runs in a reasonable amount of time here. So of course I'm using XGBoost here, and the mode here is classification because I'm predicting, is this a home run? Is this hit a home run or not? Okay, so this is the XGBoost specification, and so now I'm going to make my my workflow. I'm going to say workflow, and I'm going to say my baseball recipe and my XGBoost specification like this. And if I wanted to say what's in my workflow, I have a recipe and boost tree and is good to go. So now it is time for me to set up my racing method. Okay, so I'm going to use this package, fine tune. So this is part of Tidy Models. It just had a recent release on CRAN, so it's a good time to figure out how to use it. I'm going to use my parallel backend as per the usual. And I'm going to use this function, tune race ANOVA. So tune race ANOVA works a lot like tune grid or something, but what is different about it is instead of trying every possible parameter like every combination of trees, min n and m try on every resample. It tries all of them on a couple resamples, on an initial sort of number of resamples, and then it says, how are they doing? And if some of them are clearly worse, it eliminates them, and then it keeps going. So Tune Race ANOVA is a great for something like XGBoost, where you have a lot of tuning parameters and you don't want to keep trying them all when some of them are clearly bad. So it's great for that kind of situation. So I'm going to do the baseball folds. I'm going to try quite a lot. I don't know that I would do this during slice, but I'm not on slice right now, so I am going to do a lot. The metric that slice was being evaluated on this particular data set was log loss, so I'm going to put that in here. And then I am going to use control race so that you can see some things. I am going to, I'm just going to turn a little bit of this, set this a little bit. So let's call this my XGB result, like so. And we'll see this result here. So let me start this. So this is now going. It has to decide how many columns to use for mtry. So now what is happening here? So normally when we use tune grid, we're trying every possible parameter combination on every resample, and then we use that and we say, okay, how that now I can choose the best one. So what Tune Race ANOVA does instead is it uses like an ANOVA kind of test to to try all of the parameter combinations on some of the resamples, then test them, see how they're doing, and see if any of them are doing badly enough using a statistical test that they can be thrown out, and we don't have to keep fitting and evaluating all of them. So it's a great way to save a ton of time when you are tuning something that has a lot of parameters like this or on a lot of data. I am still tuning an XGBoost with a lot of parameters on a lot of data, so this is going to take a minute. So I am going to pause this recording and then come back to it when it is done. All right, so this has finished. We can see the output here. There's some things here to notice. It says here what metric it's using. Notice it doesn't start at the beginning and go all the way through. It says like, this is the one it started with, and then it went to this one and so forth. And when it got to, at this fold, it was able to eliminate a ton already. And by the time it got to fold 7, it was able to eliminate all but one. So all but one were clearly worse. So we have, and you can see the numbers here in the metrics, like we have 15. I said to try 15 different ones. So it tried 15 for these first 3, and then it went down to 6, and then it just had 1 here, all for the rest of these. So that's why we have those metrics there. So let us explore this a little bit. There's kind of a nice little plot here that is fun called plot race, where you can see how this works. So notice like how bad, like how clearly bad some of these are, and that then there's all these that are close together, and then eventually these get thrown away and only this bottom one is kept. So that's the one that is chosen and is kept there. So that's how the racing, so this is like the race, the plot race. This is like the race here. And then we also can do things like show best. And here, show best is actually only going to have one thing in it, because they were all thrown out except for this one here. And so this is what we get here at the end, is just this one. So if we have So this is the option that we have here at the end. We threw away everything but this one best option. So let's see. We can now update or finalize our tunable workflow with this XGB result. Let's see. So we're choosing by log loss here, and then we can fit that using last fit to the split. And so we'll say XGB last like that. And let's call, so this is like our last fit here. So we're fitting, so we're taking the tunable workflow we had, updating it with these parameters here, this many trees, mtry of this, min n of this. And so we're updating it here, and then we're fitting it one last time to the training data, and then we'll evaluate it one last time on the testing data. Once we have that here, we could do something like collect metrics on that XGB last here. That's, this is pretty good accuracy in ROC, which is pretty nice. We also, though, can collect prediction. So this, to be clear, those are metrics on the on the testing data. And so we can collect the predictions as well. And what that gives us is ability, we can, make an ROC curve, or we can compute the log loss, which is the thing we're interested in here. So we could say the true value is is home run, and then we can say pred HR like that. And so this is on the testing data, this is the result that we have, which is, close to what we had on the training data. So that is how we do use racing to tune a model. It doesn't always go all the way down to 1. It depends on exactly how different some of those values are. So those things are. So just to wrap up, let me compute some variable importance for this. So we're going to use these new extract functions, and it can extract the trained workflow from my last fit object. Whoops, like that. So here, this is a trained workflow that has a preprocessor and a trained XGBoost model in it. And then I can extract the underlying parsnib model like this, and then the VIP function knows what to do with that. We can say, let's put a little bit more than we would normally do here, maybe. And we can see like how important launch speed and angle is. The ground ball is very important, fly ball. That information about X and Z around home plate. And then we see this other info about like line drive, how fast the pitch is, and all this other information here. So this is variable importance.
All right, we used racing methods. We used tune, race, ANOVA to tune the XGBoost model on this data set about predicting home runs, predicting which hits resulted in home runs. We got pretty good results. I think most of the competitors on Slice this week who did better than this used an ensemble model. So we would need to ensemble this kind of like an XGBoost model together with either a couple of different XGBoost models or with another kind of model to do better than this probably. Racing methods are great during tuning if you, for example, have lots of different possible parameters that you want to get through with your resamples very quickly. So I hope this was helpful, and I will see you next time.